Hello, this is Mr. White, and this video is on constructing a sequence. But before we start, yesterday a student told me that when she was listening to the last video in our kitchen, her dad kept overhearing the video and he kept pointing out just how totally unfunny my jokes are. Yeah, just got real. So here's for you, Dad. Hey baby, I am so good at algebra that I could replace your x and you wouldn't even know why. Yeah, that's the good stuff. Sequences and series is where we left off, and we're still going to focus on sequences, and series are right on deck. You should know by now the difference between explicit and recursive rules for sequences. You should know the difference between arithmetic and geometric sequences. For today's example, we are going to construct a sequence given a certain criteria. In this case, the criteria are that the second and sixth terms of the sequence are 486 and 96, respectively. So let's find explicit and recursive formulas for the sequence. Now, you should first note that this is an incomplete question. There's not enough information. Do you see what information is needed to proceed? Well, we need to know what kind of sequence we're dealing with, right? We need to know whether this sequence is arithmetic or geometric. Conceivably, it could be neither, but in this video, we're going to cover both the arithmetic and geometric cases. For this type of problem, there are a number of ways you could go about it, and I'm going to just show you one that I find works well with students. I like to start by writing out a bunch of spaces for the individual terms of the sequence. And since we're told that the second term is 486, we'll write 486 in the a sub 2 slot. And we're told the sixth term is 96, so we'll fill in the a sub 6 slot accordingly. And obviously it would help us come up with a rule if we knew how those remaining slots were filled in. Well, consider that in the arithmetic case, there is a common difference. That means that every time I jump from one term to the next, I am adding a common difference, d. And when you write it out visually the way I'm demonstrating here, it's very easy to see that I'm adding 4 common differences, d, in order to get from 486, the second term, to 96, the sixth term. So we are essentially saying that a sub 2 plus 4d equals a sub 6. Therefore, 486 plus 4d equals 96. And you see that we now have a very simple algebraic equation that makes it really easy to solve for that common difference, d. Subtract 486 from both sides to get 4d equals negative 390. Divide both sides by 4 to get d equals negative 97.5. And it shouldn't surprise us that d is negative. We see from the outset that this sequence is going to be decreasing. So it's only logical that the common difference is negative. So given that the common difference is negative, I could go a step further. I'm not very far from a sub 1. A sub 1 plus a single common difference equals a sub 2. Now I emphasize a single common difference between a1 and a2. If I instead were trying to get to a sub 4, for example, I would be adding 3 common differences, right? But we're working with a sub 2 because that's the one that we were given in this case. And therefore I can plug in 486 now, as well as the common difference. A sub 1 plus 1 times negative 97.5. Let's now isolate a sub 1 to get a sub 1 equals 583.5. So now that we know the first term, a1, and the common difference, d, we're not too far away from the recursive rule for this arithmetic sequence. a1 equals 583.5 is the first part of our recursive rule. And for every term after that, a sub n equals the previous term, a sub n minus 1, and this should feel familiar from the last video, plus the common difference, negative 97.5. You, of course, could just write a sub n minus 1 minus 97.5 if you prefer. That equation is part 2 of our recursive rule, and remember to write part 3, the condition that n must be greater than 1. Those 3 parts of the recursive rule should all feel familiar from the last video. I'll put a box around that. That is our recursive rule for the arithmetic case. All right, simple enough? To get the explicit rule, I would just be largely repeating what I did in the last video, so I'm going to gloss over the process a little quickly here. For the explicit rule, if you recall, we just start writing what a sub 1 equals, and then we write a sub 2 equals that first term, a sub 1, plus a single common difference, in this case of negative 97.5. And then we write a sub 3 equals a sub 1 plus 2 times our common difference. And noticing a pattern, we jump to our general rule that a sub n equals a sub 1, 583.5, plus n minus 1 times the common difference of negative 97.5. And we put n minus 1 because we notice that the subscripts on the left side of the equation are always one more than the multiplier on the right side of the equation. So you could leave the general rule in that form, but let's go ahead and simplify it. And here is our fully simplified explicit rule for the arithmetic sequence. All right, I keep making the claim that this is very similar to stuff you've done before, and I always encourage you to keep recognizing those connections. So I want to show you that this is an analogous linear function calculation. Actually, I should show you this first. If we imagine this scenario here, being told that the second term of a sequence is 486 is kind of like being told that the input, x, for a function is 2, and that the output, y, is 486. And similarly, being told that the sixth term is 96 is, think of those as point coordinates. X equals 6, y equals 96. And arithmetic sequences are analogous to linear functions. So all the techniques you've learned in the past for linear functions may be used here for arithmetic sequences. So if you proceed to find the linear equation that goes through those 2 points, you would get a calculation that looks something like that. So you see that calculating a slope for a linear function is conceptually identical to calculating the common difference of an arithmetic sequence. Here we have our linear equation in slope-intercept form, and notice the similarities to the explicit rule for the sequence. And given that similarity, you could definitely check your work on a calculator. Type the equation into y1 and verify that the initial conditions we set out to satisfy have indeed been met. 2, 486, and 6, 96. Oh, hey Dad, what would you call it if seaweed started growing on the Little Mermaid's undergarments? Algebra. All right, constructing a sequence. Let's now look at the geometric case. We'll start out similarly. This time I'll use B to represent my sequence. We'll say the second term is 486 and the sixth term is 96. But this time, since we're treating the sequence as geometric, instead of adding a common difference to get from one term to the next, we'll multiply by a common ratio, r. So to get from B2 to B6, I'm multiplying by r 4 times. I'm not adding 4d anymore. I'm multiplying by r to the 4th power. I'm saying that b sub 2 times r to the 4th power gives me b sub 6. Or if I plug in the actual values, that gives me 486 times r to the 4th equals 96. And as I said before, this should feel kind of familiar, connected to things you've learned in the past. R to the 4th equals 96 over 486. Both numerator and denominator are divisible by 6, so we'll reduce this fraction to 16 over 81. And you should recognize that both 16 and 81 are perfect powers. I'll raise both sides of the equation to the 1/4 power to get r by itself. With the benefit of mental math, I recognize that 16 is 2 to the 4th power and 81 is 3 to the 4th power. So raising them both to the 1/4 power gives me r equals 2 over 3. That means that back up here, every time I was proceeding from one term in the sequence to the next, I was multiplying, again, not adding, I was multiplying each term by 2/3 to get me to the next term. That's what makes this a geometric sequence. Similar to what we did with the arithmetic case, I want to find out what the first term is. So I'll say that b1 times r to the 1 power gives me b2. Again, I'm trying to find b1 so that I can write my recursive rule. So we were told that b2 is 486, and we just deduced that r is equal to 2/3. Oops, that's supposed to be a times there, isn't it? Don't judge me. So if I multiply both sides of the equation by 3/2 in order to cancel out the 2/3, I get b1 equals 729. So with the first term and the common ratio, I can now write the recursive rule for this geometric sequence. Part 1 of the rule just gives the first value, b1, and every term after that just equals the previous term times the common ratio of 2/3. Again, don't forget the third part of the rule, n is greater than 1 for that equation. So that's our recursive rule for the geometric sequence. Once again, for the explicit rule, I'm going to gloss over it a little bit quickly and trust that previous lessons will enable you to hang. I start with b1 equals 729. I say b2 equals 729 times 2/3 to the 1 power. b3 equals 729 times 2/3 to the 2 power. I know the pattern. The pattern says that b sub n equals 729 times 2/3 to the n minus 1 power. I would generally just suggest you leave it right there, put a box around it, call that our explicit rule. If you wanted to take it a little further, and instead of having n minus 1 in the exponent, if you wanted to just have an n in the exponent, you could use your knowledge of exponential properties to rewrite this rule as 1093.5 times 2/3 to the n power. That 1093.5 is just 729 divided by 2/3 to the 1 power. I'll challenge you to convince yourself that these are equivalent. But definitely keep making those connections to things that you already know. This should remind you a lot of our studies of exponential functions. Think of when you were given two pairs of point coordinates and asked to find the exponential function that passes through them. That task yielded an exponential function that looked something like this. Looks a lot like the explicit geometric sequence rule we just figured out now. And likewise, that allows us to check our work in the calculator. We see that the second term is 486 and the sixth term is 96. Our initial conditions have been met. All right, real quick. You remember when solving exponential equations, how sometimes you may be tempted to use logarithms, but once in a while you can find a way to solve the equation without logarithms, as demonstrated here? Well, this problem right here reminds me of a girl I knew in high school, and that I couldn't do much more than get to second base with her. That one was for you, Dad. All right, your turn to try. Here's your exercise. Pause the video at this point. By the way, what do organic mathematicians throw into their fireplaces? Natural logs. Oh yeah, that's the stuff. All right, here are the answers. Let's see if you got these. Here are the explicit and recursive rules for the arithmetic and geometric sequences, respectively, showing on the calculator that they do check out. All right, coming up in our next episode, we'll start adding up all the individual terms of a sequence. That's called a series, and this cryptic symbol called sigma will come into play. And sigma, in case you didn't know, is named after the founder of psychoanalysis, Sigmund Freud. Good night, ladies and gentlemen.